Welcome to today's episode, where we're diving into the fascinating world of database architecture and the essential role that storage structures play in managing data efficiently. Whether you're a seasoned database administrator or just someone curious about technology, understanding how databases operate behind the scenes can really enhance your experience working with them. Throughout this episode, we'll cover some key concepts like data referencing methods, buffering, immutability, and ordering, each of which is fundamental to the performance and efficiency of database systems. Let's kick things off by exploring the two primary approaches to data referencing in databases: direct referencing and indirection through indexing. So, what does direct referencing mean? It's a method that allows databases to access data entries directly from secondary index files, which can significantly cut down on the number of disk seeks needed during read operations. Sounds great, right? However, there's a trade-off. When a record is updated or moved, the pointers also need to be updated, which can lead to increased maintenance overhead. Now let's look at the other side of the coin, using a primary index, which introduces an indirection layer. While this method can reduce the frequency of pointer updates, it typically incurs a higher cost during read operations, since the system has to perform additional lookups. For instance, MySQL's InnoDB engine uses a primary index that requires two lookups. First in the secondary index, then in the primary index. This design aims to balance the costs of pointer updates with the efficiency of read operations. Interestingly, some implementations take a hybrid approach, storing both data file offsets and primary keys. This clever strategy allows the system to validate data offsets and only refer to the primary key index when absolutely necessary, optimizing performance along the way. Now that we have a grasp on data referencing, let's consider how different workloads affect these indexing strategies. For workloads that are primarily read-heavy, updating just a couple of indexes might be enough to keep things running smoothly. However, this approach doesn't hold up as well in write-heavy environments, where multiple indexes come into play. In these cases, the overhead from frequent pointer updates can really slow things down. To address this, some systems opt for using primary keys for indirection instead of payload offsets. This shift can streamline the data location process while minimizing pointer updates, ultimately boosting performance. As we continue, let's delve into three core concepts that have a significant impact on database storage structures: buffering, immutability, and ordering. First up is buffering, which refers to how data is temporarily held in memory before it's written to disk. While every on-disk structure uses some form of buffering, the methods and extent can differ widely. For example, B-trees can leverage in-memory buffers to reduce input-output costs, a technique we'll explore in more detail later. In contrast, two-component LSM trees utilize a unique buffering strategy that combines it with immutability, showcasing the variety of approaches within storage engines. Speaking of immutability, this concept deals with whether a storage structure can modify existing data. Immutable structures, like those using append-only files, don't change previously written content. Instead, they simply add new modifications at the end of the file. This method can enhance performance and simplify recovery processes. However, some structures, such as BW trees, take inspiration from B-trees while maintaining immutability, highlighting how database design is continually evolving. Now, let's talk about ordering. The way data records are stored, whether in key order or out of order, can greatly affect both efficiency in data retrieval and the ability to perform range scans. Ordered storage makes it easier to scan records efficiently, while out-of-order storage can optimize write operations. For instance, systems like Bitcask and WhiskKey use append-only files to manage data records, illustrating the trade-offs between optimizing for write times and retrieval efficiency. Throughout our conversation, We've emphasized the importance of disk-based storage structures in contrast to in-memory systems. While both serve unique purposes, understanding their differences is crucial for effective database management. Disk-based structures are especially important for long-term data storage, while in-memory systems shine when it comes to speed and handling transient data. We've also touched on the architectural differences between column-oriented and row-oriented database management systems. These distinctions are vital for grasping how access patterns can influence database design and overall performance. In summary, today's episode has provided a thorough overview of database architecture, focusing on the essential components that contribute to effective data management. We explored various data referencing methods, the impact of different workload types, and the critical concepts of buffering, immutability, and ordering. As we continue our journey through the world of databases, these foundational ideas will serve as a solid framework for tackling more complex topics in the future. Thank you for joining us today. We hope you found this episode enlightening and that it inspires you to dive deeper into the intriguing field of database systems. Be sure to tune in for our next episode, where we'll explore B-trees and their many variants, shedding light on why they remain such a popular choice in database storage solutions. Until next time, keep learning and exploring.